Good day, everyone. We are from Home Group 3. Our project focuses on designing a digital filter to remove noise from the G3 audio signal giver. My name is Felicia Locusing, and I'll be presenting the first two phases of our analysis map, which is the sampling and the DTFT. As we know, computers cannot process continuous analog signals because of finite memory. So the first step is capture the signal at fixed intervals through a process called sampling. Using the audio rate function in MATLAB, the audio was extracted at a sampling frequency of 8000 Hz and isolated into single monochannel for accurate processing. By comparing the two graphs below, it is clear that the continuous time analog wave is successfully converted into a discrete signal. This discrete sequence is what allows for the applications of the SKEE formulas. After obtaining the discrete signal, we need to find exactly where the noise is located at. Because the noise and audio are completely mixed together in the time domain, the fast Fourier transform algorithm FFT is used to approximate the discrete time Fourier transform. This mathematical formula transforms the data from time domain to frequency domain spectrum. To keep the analysis clear, only positive frequencies are plotted to remove redundant mirrored data. Looking at the graph below, the separation is obvious. The grey region with frequency below 1500 Hz contains the desired audio, while in the red region between 2500 and 3000 Hz, there is a dense cluster of high amplitude spikes. That's the target noise. Now we have found the exact locations of the noise, we know exactly what the filter needs to remove. That's all for my part. Thank you.
My name is Lim Sin Jet. I'm going to explain Z transform and convolution. For the pole zero plot of FIR filter, although you use an 80 order dirt, but it only shows 79 poles due to pole zero cancellation. And because all poles lie at 0, the region of convolution is the entire Z plane, Z equals 0, which includes the unit circle, and it proves that the FIR filter is inherently stable. While for the IIR filter, all poles sit inside the unit circle boundary, and the unit circle is included in the region of convolution, which confirms the IIR is stable. For the convolution part, MATLAB used the filter to filter impulse response to clean up the noisy signal. This is the impulse response of FIR. The graph shows the waveform drops to exactly 0 after a sample of 80, which confirms a finite response. While for the IIR response, the waveform decays exponentially, but rings indefinitely without hitting 0. This confirms an infinite response caused by recursive feedback.
My name is Dendek. Now I will explain the FIR IIR filter design used for audio filtering. First, we look at the FIR or finite impulse response filter. FIR filters do not use feedback, which means they are always stable and have a linear phase response. So in our design, we designed an 80 order low pass filter using MATLAB's FIR1 function with a Hamming limiter. The Hamming limiter reduces the spectral leakage and also improve the filter's frequency response. So now we look, the magnitude response remains close to 0 dB from 0 to 200 Hz, meaning that the desired audio frequency passed through with almost no attenuation. After the 200 cut-off frequency, the response decreased rapidly into the stop band, effectively suppressing unwanted high frequency noise while maintaining good signal quality.
Meeting is being recorded.
So next is the IIR or infinite impulse response filter. Unlike the FIR filters, IIR filter uses feedback, allowing it to achieve a much sharper transition with a lower filter order. So in our design, we use MATLAB's Butler function to design a 14 order Butterworth low pass filter. So the design specification includes a passband ripples RP of 1 dB, which means the maximum variation of the signal is the passband is limited to 1 dB. The stop band annotation RS is 50 from the graph. The response is flat below 200 Hz, representing the desired audio signal that quickly between 200 Hz and 2.4 kHz, and strongly in a trace frequency above 2.4 kHz. In summary, the FIR filters provide excellent stability and linear phase performance, while the IR filter is more computationally efficient because it achieves similar filtering performance with a much lower filter.
I'm SKEE, and next I will explain about the result. After we sampling the DTFT and we create the FIR and IIR filter, and we have the Z transform and also the convolution, we want to see our audio output after filtered by the FIR and the IIR filter. So we use the MATLAB code here. And next one we can see from the graph. We do the frequency spectrum comparison. So the blue color one is the original input audio frequency spectrum, and you can see this part is the blue color part is the noise. So after filtered by the FIR filter, and it produced the red color frequency spectrum, which didn't include this part of the noise. So the noise is successfully being filtered, and this is a time domain comparison. So you can see it's smoother. And next one, also our IIR filter. The red part is the audio frequency spectrum after filtered by the IIR filter, and also the blue color part is the noise. So the noise is successfully being filtered out with IIR filter. Yeah, you also can see that the audio is smoother. And next, I will let my teammate to show you that the audio after filtered by FIR and IIR filter, you will see that it's smoother and lesser noise.
My name is Emily. To wrap up our filtering analysis, I will show the original audio and filter audio. Firstly, let's listen to the original audio.
0125.
You can clearly hear a loud hissing noise. On the frequency spectrum, most of the noise is between 2.5 kHz and 5.2 kHz. Next, we listen to the audio after using FIR low pass filter.
0125.
Now, the hissing noise is removed. The graph shows that the frequency above 2.5 kHz are greatly reduced. The waveform also smoother because the high frequency noise has been filtered out. So now, let's listen to the IIR filter audio.
0125. So the result is very similar to FIR filter. The useful audio below 2.5 kHz is kept, while the high frequency noise is removed. The waveform also becomes smoother. Finally, we set both filter audio files using MATLAB's audio write function. In conclusion, both FIR and IIR low-pass filters work very well. They remove the high frequency noise while keeping the original audio clear. Thank you for listening.